Hi, I'm Judy Cole, the Executive Vice President and CEO of the MIT Alumni Association, and I'm delighted to welcome you to this web production of the MIT Alumni Association.
Welcome to the MIT Faculty Forum Alumni Edition. I am David Corcoran, Associate Director of the Knight Science Journalism Program at MIT and former editor of the New York Times Weekly Science section. This is an interactive forum, so we encourage your questions. Use the Google form below the live stream to ask a question, or you can tweet one to @MITBetterWorld. We'll get to as many questions as we can. Today, we take a journey to exoplanets, faraway planets orbiting other suns, which may provide conditions just right for human habitation. Through the hunt for the perfect Earth twin, the hunt for the perfect Earth twin is now decades old. Research published this year, conducted in part at MIT, has led us to believe that rocky planets with habitable atmospheres may be as close as a mere 40 light years from Earth. Our panel today will tell us about their research and thoughts on exoplanets, field your questions, and identify just how optimistic we should be about these new findings. Panelists, let's have you introduce yourself and give an overview of your current research and your thinking on exoplanets. Zeng, why don't you start?
So hello, everyone. It's a sunny day today. So I will first give a brief introduction of myself. So I did my undergrad at MIT in course 8. And during that time, I worked with Professor Sarah Seeger on the exoplanets, and in particular on the mass-radius relation of exoplanets. So you know, this current age is the age of exoplanet discovery. From like 20 years ago, we have no planets, until now we have thousands of planets discovered. So we came to realize that so planet is a universal phenomenon that exists around almost every single star in our galaxy and also in other galaxies. So this is a fundamental question that human beings have been trying to pursue for since the civilization, that about our existence, the uniqueness of our existence in the universe. So I started working on the problem since I was undergrad, and then I came to Harvard in 2009 and did my PhD in the astronomy department here with Professor Dimitar Sasolov. So during this time, I was doing further investigation into the interior structure of these planets. And last year, I graduated from Harvard with PhD, and now I'm a postdoc fellow, Simon's postdoc fellow in the Department of Earth and Planetary Science, and working with Professor Stein Jacobson on the combining the formation theory of planetary system with the composition of planets, and trying to understand how these planets that we have discovered so far are formed. So let me just show you a brief slide. Yeah, so every time when you go out, looking into the sky, like our Milky Way, you're going to start wonder. There are so many stars up there. So because our sun is just an ordinary star, so you're going to wonder how many planets are going to be there. So the following diagram actually summarizes our current knowledge of the planets. It's a plotted mass versus radius. So it's every single planet is represented as a dot in this diagram. Mass is the x-axis and radius is the y-axis. So you can see that our Earth and the solar system planet Venus, Neptune, and Uranus are here. And all these planets that are in between, these are the planets that are that are discovered through the Kepler mission and through other efforts. So you can see that in the universe we have a range of planets out there. So today, I would welcome you to ask questions, basically any types of questions that interest you regarding these planets. In ancient India, there are 4 ways to answer questions. Number 1, giving a direct answer. Number 2, giving an answer by giving you an example or a simile. So that will illuminate the answer. Number 3, by asking you a counter question, so you would reveal the answer by yourself. And number 4 is to leave the question unsettled or subject to further investigation. So today, I will try to use all the 4 methods to answer your question. If you have any further questions, I will have you look at my personal website, which is astrozeng.com. And on this website, I give some more information about those planetary systems that we have been investigating upon, and also some other interesting stuff up here.
Great, thank you, Lee. Our next panelist is Dr. Nikku Madhusudhan, a university lecturer in astrophysics, and he joins us from the University of Cambridge in England. Madhu, welcome.
Thank you. Thanks, Dave. And hello, everyone. I am Nikku Madhusudhan, as Dave pointed out. I got my PhD in physics at MIT in 2009, also working with Sarah Seeger. And after a few brief postdocs, 1 year at MIT, 1 year at Princeton, and about 2 years at Yale University, I came to Cambridge about 3 years ago and to take up the faculty position here. Now here I lead the group on exoplanet atmospheres and interiors. That's my specialization, and that's what I'm going to tell you about today. My journey really in this field started with my PhD and happened in the most unexpected of circumstances. I was taking a class by Professor Seeger as a junior graduate student, and she posed, this was a seminar class, and she posed some unsolved problems in exoplanet science, some of the biggest questions in exoplanet science at that time. This was around 2008. And one of those questions had to do with what is now known as atmospheric retrieval. The question is as follows. If you had a few data points, a very low resolution spectrum, let's say, a few measurements of the planet's radius as a function of wavelength, it's called a transmission spectrum. If you have very low resolution spectrum, how can you infer the atmospheric composition and temperature profile and all the atmospheric properties of a planet's atmosphere by looking at its spectrum in a statistically robust way? Okay, so that was a big question back then, and I was intrigued by that question, worked on it during the course that term, and that ended up becoming my thesis. I switched immediately after the course. I switched to working with her, and that became my thesis, and that was the first instance of a spectral retrieval method for exoplanet atmospheres. And the journey continued from then on. So what I'm going to tell you about today is not the entire journey, but just a few snapshots and what is happening at the latest frontier in exoplanet science in this regime. Now, as a very big picture, Lee already mentioned that today we know just the last decade of exoplanet discoveries have taught us 2 major lessons. One is that exoplanets are extremely common, right? You go into the night sky, almost every star out there has an extremely high chance, close to 100% chance of having some kind of a planet around it. So exoplanets are ubiquitous, right? The second point that we have learned is that they're extremely diverse in their macroscopic properties, physical properties. Their masses, radii, temperatures, orbital properties are extremely diverse. So those are the 2 lessons we have already learned in the past decade. Now, what is the question at the frontier now? The question is one of the big questions is how chemically diverse are these objects? We know they're physically diverse. They're diverse in their physical properties. Now, how diverse are they in their chemical properties? And that's where that's where exoplanets come in, exoplanet atmospheres come in, because the atmospheres are our first and last stop in order to directly probe the chemical compositions of these objects. Okay, so over the past, so 2009 was when we demonstrated, Sarah Seeger and myself, in a paper demonstrated the first statistical tools to retrieve these atmospheric properties from observed spectra. And ever since, there has been a lot of work on a variety of planets in just deriving their chemical compositions, temperature profiles, and so forth, right? Sorry. So let me share with you a couple of slides which basically summarizes all the various activities I'm involved in today. Okay, so this slide shows 4 key areas that I'm interested in. The first area here is on the top left quadrant is exoplanet atmospheres. So there I'm showing you a spectrum, some of the best spectra for 2 objects, HD 189733b and HD 209458b. These are the so-called hot Jupiters, giant planets sitting very close to their stars. So their atmospheres are very hot, which means we can, the spectra are more easily measured compared to smaller planets. So that's a typical, what is called as a transmission spectrum, if you will. This is the area ratio of the planet versus the star as a function of wavelength on the x-axis. So that bump there is a water feature. So that's how we can tell that this planet, for example, has water vapor in its atmosphere. Now from that spectrum, if you notice the error bars on that spectrum, the error bars are of the order tens of parts per million. And that is incredible, is that using our current space facilities, though that's a spectrum obtained with the Hubble Space Telescope, using the Hubble Space Telescope, we are able to measure variations in the area of the planet to about 20-30 parts per million. That's incredible, if you think about it. Not only that, we go one step beyond that from that spectrum with the retrieval and the statistical retrieval tools I mentioned. From this spectrum, we are able to infer the abundance, the concentration of water vapor, also to a few tenths of parts per million in the atmosphere. Now, that is the tremendous achievement we have made in the past several years that I was referring to earlier. So we are able to measure chemical compositions at extremely high precisions today. Now, the top right quadrant is another area that I'm very much interested in, and Lee also works on that, as he mentioned, is exoplanetary atmospheres and exoplanetary interiors, and how do we tie them to geophysical properties. Only in the past year, we have made the first, this was a Nature paper actually earlier this year, where we measured the first thermal map of a rocky exoplanet, a nearby rocky exoplanet, a super Earth called 55 Cancri E. And we also have tentative evidence for variability in its atmosphere, which could be pointing towards some sort of geological activity like volcanism, but we are not sure yet, but that's work in progress. The third area which I'm interested in is shown in the lower left quadrant, which is how do we tie these chemical abundances that we're measuring in these atmospheres to their formation processes and conditions. Only in the past few years, we have again published the first papers, which basically take the abundances, the elemental abundances of oxygen, let's say, and say, can we say something about the path, the formation locations, and the migration paths of these planets through the protoplanetary disks while they're forming? Can we constrain those formation conditions based on the chemical compositions that we are seeing today? Okay, so that's a broad, very happening area right now, and the bottom right quadrant is another big area that I'm interested in general, which is how do we make the best use of these large-scale observational facilities, both in space and from ground, to make the to learn as much as we can about exoplanetary atmospheres and to connect them to their interiors and formation and so forth. So that's in short a broad summary of all the things that I'm involved in and that I'm highly interested in. Let me show you the one new initiative that I'm leading right now is called Exofrontiers. This is a think tank that has been funded by the Kavli Foundation, where for the first time we are basically saying, let's bring the community together and agree upon what the biggest questions in the field are and how best we can use our existing and upcoming resources to answer those big questions. So this is in the form, the think tank operates in the form of a series of annual symposia. The current plan is to have one symposium every year for the next decade. So every year we basically brainstorm on one big question in the field and see what are the best ways to solve that question. So I'll leave it there, but please feel free to ask me any questions on any aspects of exoplanet atmospheres, interiors, or formation, and I'll try my best to answer them. And yeah, so looking forward.
Thank you, Lee. And we are now joined by our final panelist, Jeremy Schnittman of NASA's Goddard Space Flight Center. Hi, Jeremy.
Hi, guys. Thanks, David. Thanks, Lee and Madhu, for that nice setup. So, unlike the other two panelists, I have to admit I did not take a class from Sarah Seeger. She was not my advisor at MIT. In fact, I was at MIT before she even arrived. What I did work on at MIT was actually black holes and gravitational waves. So various aspects of Einstein's theory of relativity. But at the same time, my first class as a graduate student at MIT, I remember learning about planets around pulsars, which was one of the first planets that we actually discovered. And at the time, they were really considered kind of a weird outlier. Probably had nothing to do with anything else that we would think of as planets. But it got me, it was enough to get me interested. And over the next 4 years of graduate school, I ended up taking every single class offered by Professor Jack Wisdom, who's in the Earth, Atmosphere, and Planetary Sciences Department, course 12, even though I was a course 8 grad student. And there I learned a lot about planetary formation, planetary resonances, solar system dynamics, etc. So when I came to Goddard, NASA Goddard in 2010, while I was still working a lot on black holes, I also got more interested and more involved in some interdisciplinary projects that we have going on here between the Earth Science Division, the Astrophysics Division, the Heliophysics Division, and the Planetary Science Division. So a lot of the work that we focus on here is applying models that have been developed for example, Earth science, these GCMs, the global climate models that usually make the news because they are predicting and modeling climate change, but using these models that are so full of physics details to understand more about exoplanet atmospheres, like Madhu was talking about. How can we use just even a little bit of data about the atmospheric composition of these distant planets to understand something about the climate, the weather, what it would really be like to live on these planets. And interestingly enough, just this past year, I was able to find a nice way to actually tie together some of my black hole research with the exoplanet research, courtesy of Christopher Nolan's science fiction film Interstellar, which I imagine many of you may have seen, where, as you know, they actually go to a black hole to try to find habitable exoplanets orbiting around a black hole. So at first glance, this is kind of a hokey approach to a science fiction blockbuster, and may not be related to a lot of the exoplanet science that the frontline troops are working on right now, but actually serves as a lot of very good examples of how we can go about thinking about habitability and energy sources and dynamics and all of the important questions that arise when we're studying these new exosolar planets. For example, a planet orbiting around a black hole might have a very high energy radiation, X-rays, gamma rays, ultraviolet. So it's an interesting question to say, well, whether life could exist on such a planet. And it turns out this is perhaps the question about habitability today, as we're seeing more and more planets that are orbiting very small stars called M dwarfs, and they orbit very close to the stars, so they could be exposed to very high levels of ultraviolet and X-ray flux, which, you know, life on Earth as we know it is not very, would not be very happy with this sort of environment, but perhaps life on other planets, and even the closest known exoplanet now around Proxima Centauri b could be exposed to similar levels of radiation. So it turns out to be a useful thought experiment to begin to understand what types of environments are out there and what types of environments would be habitable. Because of course this leads to all of our dreams and our fantasies about going to the closest exoplanet, going and actually exploring these in situ, which is, I think, really the ultimate goal for all of us. So I'll leave it at that and look forward to answering all the questions.
Thank you, panelists. We already have a number of questions, but I want to ask the first one, and that is the closest exoplanet that we know of is 40 light years away. Am I right?
It's closer than that. No.
4 light years.
4 light years.
So we have a recent discovery of the planet around Proxima Centauri. So that is I think is the closest one.
The title of this panel is Maiden Voyage to an Exoplanet. What would it take to physically get from here to there?
So I think there was recently a method proposed by some scientists, including Stephen Hawking, that you could laser drive a very small spacecraft, maybe the size of my pen, and you could speed that up to maybe 20% the light speed. And then you can do the simple mathematics. If the closest planetary system is 4 light years, then you are traveling at 20% the light speed. You are going to get there in 4 times 5 equals 20 years. So with the current technology, we should be able to do that. And then what you can do is you can send a series of small spacecraft, like a series of iPhones, for example. Each one of them relay the information to the one next to it. So in that way, it could get the information back to our Earth. So that is one, I think, one of the most doable methods so far.
Right. So as Lee pointed out, right, the closest exoplanet is actually around the closest star, and this is not a huge coincidence. It's very exciting, but since we now think that almost every star has or at least has planets around it, some of which are habitable, it really does make a big difference whether you're talking 4 light years or even 10 light years, 20 light years, in terms of being actually able to get information back and even have a two-way conversation. 4 years is not, is not that unreasonable for having a conversation. And in the early days of exploration, you'd set off on a ship and come back 4 years later. It was pretty doable.
Madhu, anything to add?
No, I think Jeremy and Leah covered most of the answers I would give. And generally speaking, space travel to an exoplanet is at least a century away in my humble view. But you can learn an awful lot, turns out, about their conditions just remotely. And that's what this whole biosignature research is about, astrobiology is about. Just by extremely high quality spectroscopy, we should be able to constrain a lot about the conditions on these objects within the next decade or two, I would think. And it also depends on the on the system parameters, but for the nearest objects, we should be able to get, if there are biosignatures, the first detections of biosignatures within the next 2 decades, is my view.
Okay, I'm going to go to questions from our audience. The first is from Lisa in New York City. We've talked about this some, but let's try to zero in on it. Can the panelists comment on Proxima B and their reactions to the news this year?
I mean, it's a wonderful news. I mean, it's the best we have so far, and obviously the closest planet. The next big step is how do we characterize the system further? In my view, the system doesn't transit. The planet doesn't transit its host star as yet. We haven't found a transit yet, and it may have a very low probability, less than 5%, or a few percent transit probability. If it happens to transit, we could study its atmosphere. But even if it doesn't, there are methods out there with very high resolution spectroscopy to possibly constrain the composition of its atmosphere, even if it's not transiting, just by observing its radial velocities in the near infrared. So there is some hope that with the future large telescopes, like the 30-40 meter class telescopes coming in the next decade or so, we might be able to study the atmosphere of that particular object. But the more important result that brings to the field is that there may be a lot of planets out there around low mass stars, around M dwarfs or even brown dwarfs, right? So Proxima may not be the only planet around a low mass star out there. And we have seen this with another example called TRAPPIST, TRAPPIST-1. So the general idea is that there could be a lot of such planets around small stars, which means our dream of detecting biosignatures in small planets around such planets may be closer than we think.
You mentioned transiting.
Yeah.
Can you define that term for us?
So basically, transiting means that the planet's orbit around the star is inclined in just such a way relative to the observer that you can see the influence of the planet going in front of the star by the starlight being blocked for that period when the planet is going in front. So you see a small dip in the planet's in the starlight. That particular geometry allows one to study the atmosphere of the planet when the planet is crossing the stellar surface, basically.
Viewers, if you want to know more about how these things are detected, there's a wonderful TED talk by Professor Sarah Seeger, who some of the panelists have mentioned, and she and her lab, I guess, have developed a wonderful device for blocking out starlight so you can detect the transit of the planets more easily, if I understand this correctly. Let's go to our next question, and this is from, a little hard for me to tell, wait a minute, Carl. What federal funding can you rely upon in your work? Is the European Space Agency involved too? And what about China?
Well, I guess I should start off as the NASA representative. We always want to put in a plug for funding, for federal funding, and to be honest, it actually has been quite good in recent years, and it reflects the incredible excitement of the public. Congress sees it. They've had a number of high-profile hearings about the subject, and it really is starting to flow down to money being invested by NASA. Most visible is probably the upcoming launch of the James Webb Space Telescope, the follow-on to the Hubble, which is a kind of comparable size and budget, in the $8 to $10 billion range. So this is a very, very serious investment. And now the exoplanets, well, not originally when the telescope was being designed, now exoplanet science is really one of the primary goals for the James Webb Space Telescope. And we are already now talking about the next telescope beyond that, which will do the even harder job of getting an actual direct photograph of a planet, not just looking at its shadow and as it transits, as Madhu was talking about, but what we call directly imaging these nearby exoplanets. So NASA sees this as the absolute very, very exciting area. A lot of growth in the coming years, and we're putting in the investment now.
Thank you, Jeremy. Let's move on to a question from Bill Solis in Hagerstown, Maryland. Do you believe there is intelligent life on any exoplanet, and how would that existence be verified?
So I think that is an excellent question. I once had this discussion with a professor, Charlie Lankmeyer. So he teaches a course at Harvard on how to build a habitable planet. So both he and I think that life is an inevitable consequence of planetary evolution. So not only that, not only that life is a consequence, but it's an inevitable consequence. So let me ask you a counter question. What is the most fundamental law of physics? If you throw all the other laws away, what is the most fundamental law? So I think Einstein said the most fundamental law is the second law of thermodynamics, that is the increase of entropy. So life as a phenomenon is the way that nature has come up with to maximize its entropy production and to maximize the rate of entropy production. Let me give you an example. If I have a cup of tea, I let it sit in the air, which is full of oxygen, but without any bacteria. This tea will be oxidized on the order of weeks. Now, if I leave this tea in the air in our Earth that has bacteria, the bacteria is going to find that potential energy and to use that potential energy to generate more entropy. So it's going to break it down overnight. So any tea overnight, you should not drink it. However, if I, as a more complex life, drink this tea, I break down that within the order of hours. So in fact, life is the way that universe come up with to maximize its entropy production. And during this process, we build up complexity. But this complexity is at the expense of a much more entropy production. So it is a transient phenomenon. It's a transient phenomenon. So just as what Buddha teach or what Buddhism teach, anything, any form, any phenomenon is transient. It's not going to last forever. Everything is impermanent. So that's why we think that life and also the intelligent life to a higher complexity is driven by this high quality energy flow from the sun, which is radiating at 6,000 Kelvin black body temperature. And we're consuming this higher quality energy and reducing that to a lower quality energy and radiating out at the temperature of our planet, 300 Kelvin. And during this process, we generate a lot of chaos, entropy. And we use a little bit of that to generate order, complexity. So that is my answer.
Well, I'll take a quick stab again at the funding point of view. It's an unfortunate problem that government funding, NASA funding, is somewhat risk averse, which is why NASA is not funding huge projects to go out and search for ET. In fact, if you look at the total amount of federal funding spent on the SETI, the Search for Extraterrestrial Intelligence program, I believe it's less than the movie Contact grossed. Whereas if you look at the amount of money spent on Mars exploration in the last 20 years since that little rock was found from the Allen Hills meteorite with something that might look kind of like a bacteria in it, kind of the science approach has spent over $20 billion on Mars exploration. So from that point of view, I think NASA is taking the strong, dedicated, yet safe route. As far as the future of SETI and dedicated searches for extraterrestrial intelligence, in the immediate future, I think we're going to have to rely on private. And
Madhu, would you like to add anything to this question of intelligent life?
Yeah, I mean, clearly, I cannot comment on whether there is intelligent life because we don't have any observational evidence for it. But just based on statistical arguments, I think it's got to be out there. How we find it, when we'll find it, is a matter of technical detail, in my view. But just 10 years ago or 20 years ago, we didn't know of any planet. If you take 20 years ago, roughly, we didn't know of any planet outside the solar system. And today we know that the frequency is 100%. Almost every star should have a planet. And what is more, based on the last decade of discoveries, we know that the smaller planets are the most abundant. So habitable planets should be out there in tons, very common. So I don't see why, if you have those many habitable planets out there, I don't see why intelligent life should be all that rare. So I don't doubt that there is, just based on these numbers that we are seeing, that there should be intelligent life out there. Now, how do we go about searching that is a very different question, and that's where all the practicalities come in. Like Jeremy pointed out, the primary one being funding, because there is a lot of funding that needs to go in to answer that particular question.
Well,
but before that, I think we take this more immediate shortcut, which is more accessible, is this idea of finding their atmospheric signatures and see if they have biosignatures in their atmospheres. So that's going halfway on that path.
Definitely lots of intelligent life in both Cambridges and Upper Manhattan. Here's a question from Jean Leary in St. Cloud, Minnesota. Will the discovery of gravitational waves impact or aid your work?
This is definitely my wheelhouse. This is the most exciting discovery of my career, and it's something that I've been working towards and looking forward towards for the last 20 years. So it's been tremendously exciting. How much it affects specific exoplanet science, not a huge amount, but probably more than you might think. Because really every time a scientific discovery is in the news, especially one that comes out of a large collaboration like the LIGO collaboration that's been funded by the NSF, it really generates a very important positive, very, very positive support for science, and sees the power of discovery when we work together. So I think it's been a fantastic discovery, and I think it actually does have a direct positive impact on all branches of science, including exoplanet science.
I'm told that we have just 5 minutes, and I want to try to get to these remaining questions. So from Steve Brody in Arlington, Virginia, is there a role, and if so, what, that you can envision for the search for evidence of life on an exoplanet for SOFIA, the 747-based airborne telescope?
That's a very interesting question. SOFIA does have some near-infrared channels which we can use to do spectroscopy. So I am part of a program on SOFIA, and the data are still being looked into. SOFIA can be sensitive to large planets, like these hot Jupiters we have been talking about, large and hot planets very close to their stars. But for small planets where we are looking for habitable, for biosignatures, SOFIA, I don't think, has the sensitivity to detect biosignatures in Earth-sized planets.
Thank you. Here's a question from Jim Heiss, or Heisey, from Marlborough, Massachusetts. What ethical implications do you think discoveries like this will have on how we treat our own planet?
So I think this is also a very important question to ask. So when we look at our planet, we know that there are many planets out there, but our planet has the unique condition, has the necessary condition for life. It has just the right amount of water. So that means it has not too much water to cover all the continents. So if the planet is entirely covered by water, it is likely that you will not have this feedback of mechanism to bury carbon dioxide in the atmosphere. So it will have a runaway greenhouse effect. It also has enough water to sustain life. So planet is a universal phenomenon, but the necessary conditions for it to have life is also comparatively rare. So that means we should cherish our planet.
Just to jump in, a quick answer also on that is related to the search for intelligent life has been long based on something called the Drake equation, which kind of breaks down all of the uncertainties in how to find life around other planets. And it's really remarkable in the last 20 years, we've made so much progress on probably about half of the terms in the Drake equation, finding, the fraction that stars that have planets, the fraction that have habitable planets, etc. The big last variable in the Drake equation has been the lifetime that an advanced technological society can survive. And this has long been the big question mark that we can perhaps answer by looking out and then apply that answer back to us, because I'm sure we would all be much happier if we knew that the expected lifetime of a civilized, technologically civilized civilization would be more than a couple hundred years. And this may actually be testable by looking for others.
Yeah, I totally agree with that. So if you realize that any civilization, any life form, any planet is not going to last forever, it's transient, then you will generate the loving kindness to cherish that, to make sure that it will last slightly longer.
Those are all the audience questions we have time for, but I'm wondering if any of you panelists, Jeremy, Madhu, Lee, have a question for any of the others.
No.
Okay.
Just make sure to send your questions to us by email too. We love getting questions. I'm sure I can speak for the other panelists to say that.
Absolutely.
And share your excitement and curiosity with everyone. And that's how we move forward together.
Yeah. Now I would like to end this by saying that we are really in one of the most exciting times in astronomy. I think, like, just the last 20 years, this explosion we have seen in this field. I think this may be the best time in science. And in the next, decades, we might, this field is full of surprises. So in the next decades, we might even detect the first biosignatures and evidence for life and along other things along those directions. So I think just as scientists, the public and everyone is super excited about this area, and we want to keep that excitement going. So I'd like to thank everyone for their interest, for all the audience for their interest in this subject and joining us today.
I have to say that I was somewhat skeptical of the title of this panel discussion, Voyage to an Exoplanet, but I'm not skeptical anymore. It's a great discussion. Thank you. Thank you all very much. On behalf of the Alumni Association, I want to thank everybody for tuning in to this Faculty Forum Online Alumni Edition. Thanks again to our alumni panelists from Harvard, University of Cambridge, and NASA. We didn't get to all the questions submitted, but rest assured our panelists will see them all. Tweet about today's chat using the address at MIT Better World or hashtag MIT Better World, and send follow-up questions or feedback to alumnilearn@mit.edu. Thanks again for watching.
Thanks again for joining us. For more information on future MIT Alumni Association productions, please visit our website.